Hey guys, welcome back to another session on vectors. So today we'll be looking at some of the features of vectors being parallel, as well as we'll be touching a bit on collinearity. Now let's begin with vectors being parallel. Now on screen, I have written two vectors OP being equal to 3, -2, and QR being equal to 6, -4. Now, how do we test whether two vectors are parallel? Well, it's rather easy. The aim is to simplify your vector to its lowest form by trying to pull out a constant from within brackets. So for example, in this first vector OP, you can see that 3 and -2 do not share any common factors. So it seems to be reduced as simple as possible already. And let's look at QR. So a common factor between 6 and -4 is 2. So if we were to pull out that common factor 2 in brackets by a process of division, we would be left with 3 and -2, such that if we were to expand again, you would get 2 multiplied by 3 as well as 2 multiplied by -4. That gives us back our original vector. So after simplifying our vector, one thing you would observe is that both our vectors that are contained within the brackets are exactly the same. This is how we find or determine if two vectors are parallel. We can simply reduce very large vectors, and if the vectors can be written as scalar multiples of each other, then they are said to be parallel. Let me do another example. Okay, so example 2. Let's just say we had a vector OT, and that was equal to, let's just say 6 and 9. And then we had a second vector SR, and that was equal to, let's just say, I want to choose a large number here, 12 and 15. Let's try and see what will happen here. So notice in both cases, we have vectors which can be simplified. So let's try and see what happens. So the first common factor I'll pull out from the vector OT is 3. And I'll end up getting 2 and 3 remaining within bracket. And 2 and 3 can't be simplified any further. There are no common factors. So I'll move on to my vector SR. So let me try to pull out a common factor between 12 and 15. Let's pull out 3. So if we were to pull out 3, we'd end up getting 4 and 5. Now, notice that after carefully factorizing, what's contained inside our brackets are not the same. Therefore, in this case, even after simplifying our vectors to the lowest form, we have found that the vector OT is not parallel to the vector SR. So for two vectors to be parallel, they must definitely have a commonality within those brackets, which is the vector part, and written outside these values They are just scalar products or scalar multiples of that vector outside. And those numbers can vary. They can be different. It would not affect the vector being parallel. So I hope that clears up any issues you guys may have with vectors being parallel or not. So we are going to take some of this concept and we are going to move forward into yet another concept of vectors called collinearity. Now, for those of you who've ever heard the word collinearity before, it typically means lying on the same line. For example, if I were to draw on screen here a straight line, and on that straight line, I were to highlight 3 points, and I were to call my points O, A, and B, you can clearly see that those 3 points lie on the same line. Now, what if I were to break up these vectors that lie on this line? For example, on this line, if I were to place arrows here and here, that would mean we have the vector OA, as well as we also have the vector AB. Now, let's just say that the vector OA was equal to 1, 2. And the vector AB had values 2, 4. Now, if I were to ask you, are the vectors OA and AB parallel to each other? Well, then we can go ahead and test it. We can see that the vector OA, which is equal to 1, 2, has been reduced as much as possible. So let's try to reduce the vector AB. We can factor out 2 such that we get 1, 2. And within brackets, you can see we have ended up getting the same thing. Therefore, we can safely say that the vector OA is definitely parallel to the vector AB. Now, if two lines are essentially parallel to each other, and you were to draw them on a diagram, then they should look like this. If OA is a vector and it's parallel to another vector, AB, then if you had to represent it on a diagram, it should essentially look like this. But you see, there's a problem. These two vectors contain a letter in common. Can you identify the letter that's in common? That's correct. These both vectors contain the letter A. Now, if they both contain the letter A, how is it possible that these lines are not joined? You see, for collinearity to take place, it means that whenever two vectors are parallel to each other, but they contain a letter that's in common to both lines, then the only possible way for us to draw this information on a diagram would be by representing these 3 points on one straight line. That way, the vectors are definitely parallel to each other. As you can see, all lines that lie on the same line, or all segments of a line rather, they would be parallel to each other. They follow the same direction, the same inclination, as well as if they must contain a common letter or a common part, then they should belong to the same line. So collinearity only takes place if two conditions are met. The first condition for collinearity to happen must be that the two vectors you are considering happen to be parallel to each other. So I'll write that down. The two conditions for collinearity are that the vectors you are considering must be parallel to each other, and the second condition is that those two vectors must contain a common letter. That tells us that they all lie on the same straight line. So I hope that clears up whatever misconceptions you may have ever had about collinearity. And as I do some worksheets later down, you will see the concept pop back up. So let's move forward. Okay, so we are going to attempt to do some questions by applying some of the concepts we have just learned from this session as well as previous sessions. So our question goes like this. What if we have two vectors, OP and OR? As you can tell, they both start from the origin, so these are position vectors. So OP and OR are position vectors with respect to the origin. Now, they're also telling us that P, just P, is the point 2, 7. Now, you guys can clearly recognize that when a point is written horizontally, it's just simply a coordinate. It's no big difference. It's not a vector. It's just a point, aka coordinate. And then they went on to give us information that the vector PR is equal to 4, -3. So they are asking us some questions. The first question they're asking us is to find OP. What is OP equal to? Now, browsing through our question, we do have a bit of information that we can use. The first bit of information we can use is that P, the point, is given by coordinates 2, 7. And if you can recall from previous videos, a coordinate simply has to be written as a column, and it becomes a vector by writing O in front of your letter. So that part A was really easy. Now let's move on to part B. They want us to find OR. Now, in this question, as you search throughout the words, there is no point R, so getting the vector OR is a bit more difficult. We must work for it. So how can we work? What else are we given to use? Well, they have given us the value PR. Let's see what we can do with PR. So they have said that PR is given by 4, -3. We can see that part of what we want lies in the vector PR. What else do we know about vectors? Well, we can use vector rules to separate a vector that is not a position vector. For example, the vector PR can also be written by separating it into the difference of two position vectors, where we have the second letter subtract the first. Review my video on vector rules if you need to see and understand how we arrived at this. Okay, so now that we have, oh, this is supposed to be Q. I'm sorry. This is not supposed to be Q, it's supposed to be R. What's happening to me? Okay, guys, sorry about that. Okay, so we have used our vector rule to break up our vector PR into OR, subtract OP. Now, I can see something. They want us to calculate the value of OR, and here it is. So what we are going to do is we are going to consider this statement as an equation, and we are going to make OR the subject. Making OR the subject simply means carrying across our negative OP on the opposite side of our equal sign, such that we will get OR is equal to PR plus OP. Now that I have carried across OP towards the same side as PR, we can see that we actually have values for PR and OP. So we will write them in. PR is given by 4, -3, and OP is given by 2, 7 from part A. And now we simply add. 4 plus 2 is 6, and -3 plus 7 gives us 4. And therefore, the vector OR has worked out to be equal to 6, 4. Sorry, 6, 4. There's no comma. All right, guys, so I know this question may seem a bit tasky, a bit tricky, and you're worried that if it comes in exams, you're not going to know to use the vector rule. But strangely enough, most vector questions entail the use of this rule. So whenever you are caught in a bind and you realize you're getting nowhere, try the vector rule. Try breaking up some position vectors into the difference of 2. See what happens, see what you have. And believe it or not, 90% of the time, it usually ends up being the way towards getting your answer. Okay, so let's look at another question. I think I have one more on screen. Okay, so look at this question here. They want us to find RS. Now, once again, we can try to apply our vector rule, and we can split RS into OS, subtract OR. Do we have values for these? Yes, we do. From this coordinate or point, we can create a vector for OS. And now we will simply substitute that value here. And then from previous parts, part B, we found the vector OR to have values 6 and 4. So now it's just a simple matter of subtracting. 14, take away 6, that gives us 8. And a -2, subtract 4, gives us -6. So there you have it. That's our answer. Nice, simple, and easy. Let's move on. And we have a question here on collinearity. So they want us to show that 3 points are collinear. What does this mean? It simply means that the points P, R, and S lie on the same straight line. Now, how can we begin to show that these 3 points are collinear? Well, the first thing we can do is create 2 vectors using those 2 points. So I will create the vector PR as well as the vector RS. Now, do we have values for those vectors? Let's move up and see if we calculated these. So we do have RS being 8 -6. And I believe from part A, we got PR as 4, -3. That's 4, -3. Right. So we have already developed two vectors that lie on our straight line. Now let's start reducing these vectors to check to see if they are parallel to each other. Because remember, our conditions for collinearity are 1, they must be parallel, and 2, they must contain a common letter. Now the first vector has already been reduced to its simplest form. In the second vector, RS, we will factor out 2. Factoring out 2, we get 4, -3. And clearly, you can see that these two vectors are the same. Therefore, we can say, first point, the vector PR is definitely parallel to the vector RS. Now, testing for collinearity, they must contain a common letter. Now, PR and RS both contain the letter R. So therefore, R is common. Because our two conditions of collinearity have been met, therefore, we can say that the points R, P, and S are collinear. You can also include a statement. You can say, therefore, P, R, and S are collinear. Remember, at the end of the day, examiners cannot read your minds when they're marking your papers, so it's definitely always worth it to make sure you write down all your explanations pen to paper instead of keeping them up in here in your minds. Okay, guys, so I wish you all the best. If you would like to see more questions like these, be sure to comment down below, and I'll definitely do a full tutorial for you guys. Okay, so see you soon. Don't miss my next lesson. It may be on vectors again, or I might be doing a short tutorial session by request on simplifying algebraic expressions. So either way, look forward to seeing you guys soon. Bye.